the ladder. Okay, right. We've got issues here because if this person moves, things change. Because if the man moves further up the ladder, and you consider that what's happening is, as he does that, he's exerting a greater moment on the ladder here, because he's moving further away from this pivot point, there would be more force from the ladder pushing into the wall at A. And what that would mean is, if you're pushing into the wall with more force at the top of the ladder, there would be more reaction force coming back at you from the wall. If you consider, if you're stood at the bottom of the ladder, it's really easy to wobble that ladder and make it rattle against the top of the wall. If you're stood at the top of the ladder, don't do it, but it's really hard because you're exerting so much turning force by your weight being on there. So the reaction at A is going to change as a result of the man moving. So we need to think, okay, we're going to have to redraw this diagram. So, new diagram for part B. Smooth wall, rough ground. We have point B and we have point A. We still have our mass of 40 kilograms, which means we have a weight of 40 G. But now, our weight of 85 G is now stood at the top of the ladder. As mentioned, that has caused the reaction force at A to change value. We still have a frictional force acting in that direction there because the ladder is wanting to slip to the right. We still have a reaction at B. We are trying to calculate the coefficient of friction. We don't know that, but we do know that the angle of inclination is still 58 degrees. Okay, so what hasn't changed? Well, the total force up is still the reaction at B. The total force down is still the total mass of, total weight, I should say, sorry, of the man and the ladder itself. So the reaction at B is still 1,225 newtons. However, the reaction force at A has changed, which means the amount of friction must have changed, because it is still the case that the reaction at A is equal to friction, because they are the only two forces acting horizontally. So park that there for a moment because I need a big long line now from a moments equation. I'm going to do the same again. I'm going to do moments about B. So clockwise, it is still reaction at A times by 12 sine 58. Because it's still reaction at A, that's still 12, it's the length of the ladder, that's still the opposite side, line of action of the force, pivot, that's still the same. The other thing that hasn't changed is the 40G. So 40G is still times by 6 cos 58, because the hypotenuse is still 6, and we're still after this length here, which is perpendicular to the line of action of the force. What has changed is the 85G is no longer 7 metres away from where we're pivoting, it's now the full 12 metres away. So this distance here, perpendicular to the line of action of the force, it's no longer 7 cos 58, it's now 12 cos 58. But again, works the same way. My reaction at A times by 12 sine 58. And collect all those terms together as I did before. 40 times 6 is 240, plus 85 times 12 means I've got 1260 G cos 58. That's a number, so I'm going to do that number there, 1260 times 9.8 times cos 58, divide it by 12 sine 58 to get my reaction at A to be 642.99. I'm going to store that in my calculator because I'm going to need that in a minute. And I know that the reaction at A is equal to the force of friction. So I can now say that friction is also 642.99. Now the question was asking me for the coefficient of friction, so at this stage I'm going to need to use that maximum friction is equal to mu times r. I've got my maximum friction to be 642.99 equals mu times by the reaction. Importantly though, it's the reaction at B, because that's where the friction's happening, not the reaction at A. The reaction at B I had already as 1225 newtons. So if I do this number here, 642.99 divided by 1225, I get mu to come out as 0.52489. So my coefficient of friction is 0.525 to three significant figures. So, reviewing part B, I drew a new diagram. Some things were the same, some things had changed. The fact that the man had moved meant that the reaction force at the wall had changed, because moving up and down the ladder changes the amount of force that the ladder is pushing into the wall. But again, it's a statics question. We resolved vertically, we resolved horizontally, and we did a moments equation. It's the same three things each time. That's your strategy. Vertical, horizontal, moments. Always the same. One of those three things will get you closer to what you need. Doesn't matter what order you do them in. So, we worked that all the way through, and then we used that friction was mu times reaction force, using the reaction force at B because that's where the friction was happening, and then we got our value for mu. Job done.